Square frame of side L is dipped in a soap solution. When it is taken out of the solution, a film is formed on it. If the surface tension is T, then the force acting on it is A 2TL, B 16TL, C 4TL, and D 8TL. Now we know the surface tension is given by the formula work done upon the area or force upon the total length. Therefore, now the force acting on single side is equal to 2TL, since the surface tension occupies twice the area or twice the length. Therefore, the force acting on four sides will be equal to 4 into 2TL, which is 8TL. Here we take four sides because it's a square frame. Therefore, here the correct answer is option D. Rises in a height to a height of 10 centimeter in the capillary tube, and mercury falls to a depth of 3.42 centimeter in the same tube. If the density of mercury is 13.6 grams per cc and the angle of contact is 135 degrees, then the ratio of the surface tension of water and mercury is now 0. Now the glass and water is 0 degrees Celsius and cos 135 is given here. Now here are the options. Now we know that the tension is given by 2 into h into rho into g upon 2 cos theta. Sorry, not here. H will get r into h into rho into g upon 2 cos theta. Therefore, T of water upon T of mercury will be given as r into hw into rho w into g upon 2 cos theta 1 into 2 cos theta 2 upon r into hm into rho m into g. Therefore, on substituting the values, we'll get 10 into cos 135 degrees upon 3.42 into 13.6, which is equal to 1 by 6.58, which is 1 is to 6.58. Therefore, the correct answer is option D. Spherical drop of water has a diameter of 2 millimeter. If the surface tension of water is 17 to 10 is to minus 3 Newton per meter, then the difference of pressure between the inside and the outside the spherical drop is either A 70 Newton per meters, B 90 Newton per meter square, C 110 Newton per meter square, or D 140 Newton per meter square. Now, the excesses of pressure in a water drop is given by the formula as 2T upon R. So all we got to do is substitute the values of T and R and we'll get the answer. Therefore, pressure is equal to 2 into 70 into 10 raised to minus 3 upon 2 millimeter, which is 10 raised to minus 3. Therefore, we'll get the answer as 140 in newtons per meter square. Therefore, here the correct answer will be option D. Pure water rises through a height h in a capillary tube of internal radius r. If T is the surface tension of water, then the pressure difference between the water level in the container and the lowest point of the concave meniscus is either T upon R, R upon T, 2T upon R, or R upon 2T. Now, for the capillary rise, R into H into rho G is equal to 2T cos theta. And the pressure difference dP is H into rho into G, which is equal to 2T cos theta upon R. Now, since it is water, we know that the cos theta for water is always 1. Therefore, the difference in the pressure is 2T upon R. Therefore, here the correct answer will be option C. Is the work done when a bubble of volume V is formed from a solution? How much work is required to be done to form a bubble of volume 2V? Now, V, which is the volume, is equal to 4 upon 3 pi R1 cube. This is the volume of the first bubble. Now, for the second bubble, V is doubled. Therefore, 2V is equal to 4 by 3 pi R2 cube. Therefore, R2 cube upon R1 cube is equal to 2. Therefore, R2 upon R1 is equal to 2 raised to 1 by 3. Now, the work done will be equal to the surface tension into the area. Therefore, W dash upon W will be equal to T into 4 pi R2 square into 2 upon T into 4 pi R1 square into 2, which is equal to, means 2 will get cancelled and T will also get cancelled. We get as R2 square upon R1 square. which is equal to 2 raised to 1 by 3 the whole square, which is equal to 2 raised to 2 by 3. Therefore, W dash will be equal to 4 raised to 1 by 3 W. Therefore, here the correct answer will be option D. Work of 3 into 10 raised to minus 4 joules is required to be done in increasing the size of a soap film from 10 centimeter into 6 centimeter to 10 centimeter into 11 centimeter. The surface tension of the film is 1.5 into 10 raised to minus 2, 5 into 10 raised to minus 2, 3 into 10 raised to minus 2, or 6 into 10 raised to minus 2 Newton per meters. Now, we'll first find out the area or the change in the area. dA is given by 10 into 11 minus 6, since it changes from 6 to 11. Therefore, we'll get dA as 50 into 10 raised to minus 4 meter square. Therefore, the surface tension T will be given by E upon 2 dA, which is equal to dW. Energy is work done, which is 2 dA. Therefore, T will be equal to 3 into 10 raised to minus 4 upon 2 into 50 into 10 raised to minus 4, which is given by 3 into 10 raised to minus 2 Newton per meter. Therefore, here the correct answer will be option C. The surface tension of a liquid is 5 into 10 raised to minus 2 Newton per meter in the SI system. In CGS system, it is expressed as either 5 into 10 raised to 2, 5 into 10 raised to 5, 5 into 10, or 5 into 10 raised to 4 dyne per centimeter. Now, in SI system, the surface tension is 5 into 10 raised to minus 2 Newton per meter. In CGS system, Newton gets converted to dyne and meters gets converted to centimeters. Hence, the value will be in dyne per centimeter. Now, hence to convert newtons into dyne, we multiply it by 5 into 10 raised to minus 2 into 10 raised to 5. And to convert meter to centimeter, we multiply it by 100, which is 10 raised to 2. If on calculation, we'll get an answer as 5 into 10 raised to 1 dyne per centimeters. Therefore, here the correct answer will be option C. The surface tension of soap solution is 30 dyne per centimeter. A soap bubble made from this solution has a radius of 1 centimeter. The work done in doubling the radius of the soap bubble is either 1131 ergs, 2262 ergs, 3300 ergs, or 800 ergs. Now, we know that for a soap bubble, we multiply the area into twice, as there are two free surfaces. Therefore, the surface tension is given by T is equal to the work done upon the area. Therefore, we need to find the work done in doubling the radius, which is equal to T into dA into 2, which is equal to T into 4 pi into 4r square minus r square into 2. Therefore, dW is equal to 24 pi r square T. Therefore, the work done is 24 pi r square T. Therefore, on substituting the values of pi, r and T, we'll get the answer as 2262 ergs. Therefore, the correct answer here is option B. A spherical drop of water has a diameter of 2 millimeters. If the surface tension of water is 70 into 10 raised to minus 3 Newton per meter, then the difference of pressures between the inside and the outside of the spherical drop is 70, 90, 110 or 140 Newton per meter square. Now, the excess of pressure in a water drop is given by 2T upon R. Therefore, P excessive is equal to 2 into 70 into 10 raised to minus 3 upon 10 raised to minus 3, which is equal to 140 Newton per meter square. Therefore, here the correct answer will be option D. The excessive pressure inside the soap bubble of volume V1 is twice the excessive pressure inside the second soap bubble of volume V2. The value of the ratio V1 upon V2 is either 1 half, 1 by 4 or 1 by 8. Now the excessive pressure P is given by 40 upon R. Therefore, 40 upon R is equal to twice into 40 upon R2. This is R1. Since it is given that V1 is twice excessive pressure of V2. Therefore, R1, R2 will be equal to twice R1. Therefore, and V1 is equal to 4 by 3 pi R1 cube, and V2 is equal to 4 by 3 pi R2 cube. Therefore, we will get V1 upon V2 is equal to R1 upon R2 the whole cube, which is R1 upon 2 R1 the whole cube, which is 1 by 8. Therefore, here the correct answer will be option D. Air is pushed in a soap bubble to increase its radius from capital R to 2R. In this case, the pressure inside the bubble A becomes 0, B increases, C decreases, and D does not change. Now, the excessive pressure in a soap bubble P is given by the formula 4T upon R. So we can say that P is inversely proportional to R. Thus, if the radius of the soap bubble is increased, if R is increased, P will obviously decrease. If R was decreased, P would increase. But in the question, radius R is increased, therefore P will decrease. So here the correct answer will be option C, decreases. Two glass plates separated by a distance 1 millimeter are kept standing in a water tank. The height to which water will rise between the plates is approximately equal to. Here are the options. Now the surface tension of water is given as 72 dynes per centimeter. Now we know that the force due to surface tension is given by the weight of the liquid column. Therefore, 2T L plus B is equal to mg. Therefore, 2LT is equal to length into breadth into height into the density into G. Here, B is neglected on the LHS. Therefore, 2 into 72 is equal to H into 0.1 into 1 into 980. Which is therefore H is equal to 144 upon 98, which is 1.45 centimeters. Therefore, here the correct answer will be option B. The height up to which water will rise in a capillary tube will be A. Minimum when the temperature of water is 4 degrees, maximum when the temperature of water is 4 degrees, minimum when the temperature of water is 0 degrees, the same at all temperatures. Now, H is inversely proportional to the density. Therefore, if density decreases, H will increase. Therefore, for H to increase, density should be the minimum. Now, the density of water is maximum at 4 degrees Celsius. Therefore, if density is maximum at 4 degrees Celsius, therefore the height will be minimum at 4 degrees Celsius. Therefore, here the correct answer will be option A, minimum when the temperature is 4 degrees Celsius. 125 raindrops are combined to form a single drop. The ratio of the total energy of 125 drops to that of a single drop is. Here are the options. Now let the radius of the small raindrops be r and the big raindrop formed be capital R. Therefore, 125 raindrops, that is 125 into the volume of the small raindrops, is equal to the volume of the big raindrop. Therefore, capital R is equal to 5R, or small r upon capital R is equal to 1 by 5. Now, therefore, the ratio of the total energies S1 upon S2 will be equal to 125 into R upon capital R the whole square, which is equal to 125 into 1 upon 25, which is 5. Therefore, here the correct answer is option B. A film of water is formed between two straight parallel wires, each of length 10 cm and separated by 4 mm. How much work should be done to increase their separation by 1 mm while still maintaining their parallelism? Here, the surface tension is given as 7.5 into 10 raised to minus 2 Newton per meters. Now, we all know that the work done is given by the formula 2T into the change in the area. Therefore, on substituting the values, we'll get 2 into 7.5 into 10 raised to minus 2, 10 into 10 raised to minus 2 into 1 into 10 raised to minus 3. Therefore, on calculation, we'll get 15 into 10 raised to minus 2 into 10 raised to minus 4, which is equal to 1.5 into 10 raised to minus 5 joules. Therefore, here the correct answer will be option C. Water rises in the capillary tube up to a height h, so that the upward force due to surface tension is balanced by the force due to the weight of the water column. If this force is 90 dyne and surface tension of water is 6 into 10 to minus 2 Newton per meter, then the inner circumference of the capillary must be, here are the options. Now, the upward force due to the surface tension is given by 2 pi r into t, which is equal to 90 into 10 raised to minus 5 newtons. Therefore, 2 pi r is equal to 90 into 10 raised to minus 5 upon t, which is equal to 90 into 10 raised to minus 5 upon 6 into 10 raised to minus 2, which is 15 into 10 raised to minus 3, which is equal to 1.5 into 10 raised to minus 2 meters. Therefore, here the correct answer will be option B. One is the work done in blowing a soap bubble of radius r from a soap solution at room temperature. The soap solution is then heated and second soap bubble of radius 2r is blown from the heated solution. If W2 is the work done in forming the second bubble, then here are the conditions. Now, the work done in forming a soap bubble of radius r is W1 is equal to 8 pi r square T1, and the work done to form a soap bubble of radius 2r, which is W2 is equal to 8 pi into 2r the whole square into T2, which is equal to 832 pi r square T2. Therefore, the ratio will be W2 upon W1, which is equal to 32 pi r square T2 upon 8 pi r square T1, which is equal to 42 upon T1. Now, if T2 is equal to T1, therefore W2 will be equal to 4W1. But it is given that the solution is heated. As the temperature is increased, the surface tension of the soap solution decreases. Therefore, T2 is more than T1. Therefore, W2 will be less than 4W1. Therefore, here the correct answer is option D. The radius of a soap bubble is 4 times that of another, then the ratio of excessive pressure will be 4 is to 1, 1 is to 4, 16 is to 1, or 1 is to 16. So let R1 and R2 be both the radiuses. Therefore, it is given from the question R1 is equal to 4R2. Therefore, the excessive pressure delta P is given as 4T upon R. Therefore, the ratio of delta P1 upon delta P2 is equal to 4T upon R1 into R2 upon 4T, which is equal to R2 upon R1, which is equal to 1 by 4. Therefore, the correct answer here is option B. Two soap bubbles of equal radii, R and R, coalesce, then the radius of curvature of the interface between the two bubbles will be A0, B2R, C R by 2, and D infinity. Now, for two soap bubbles of radii R1 and R2, where R2 is more than R1, the radius of curvature of the common interface is given by R is equal to R1 R2 upon R2 minus R1. But in this case, R1 is equal to R2. Therefore, R2 minus R1 will be 0. Therefore, R will be R1 R2 upon 0, which is infinity. Therefore, here the correct answer will be option D. A water drop of radius capital R is split into n smaller drops, each of radius small r. If T is the surface tension of water, then the work done in this process is, here are the options. Now, the volume of one drop is equal to the volume of n drops. Therefore, 4 by 3 pi r cube is equal to 4 by 3 pi small r cube into n. Therefore, r cube will be equal to n into small r cube. Now, the change in area delta A will be given by 4 pi r square n minus 4 pi capital R square, which is equal to 4 pi n small r square minus capital R square. Therefore, dA will be given by 4 pi nr cube upon r minus r square, which is equal to 4 pi r cube upon r minus r square. Therefore, dA will be equal to 4 pi r cube 1 upon r minus 1 upon capital R. Therefore, the work done will be tension into dA. Therefore, 4 pi r cube T 1 upon small r minus 1 upon capital R. Therefore, here the correct answer will be option C. A mercury drop of radius capital R breaks into n droplets of equal size. The radius small r of each droplet is, here are the options. Now we know that volume of one drop is equal to volume of n drops. Therefore, 4 upon 3 pi capital R cube is equal to n into 4 pi small r cube upon 3. Therefore, r cube, capital R cube is equal to n into small r cube. Therefore, taking cube root on both sides, we'll get n raised to 1 by 3 into small r. Therefore, r square is equal to r is equal to r upon n raised to 1 by 3. Therefore, here the correct answer will be option B. Mercury drop of R splits up into 1000 droplets of equal radii. The change in the surface area is 8 pi r square, 36 pi r square, 12 pi r square, or 40 pi r square. Now we know that volume of one drop is equal to volume of n drops. Therefore, applying the relation, we'll get the relationship between the small r, which is equal to small r is equal to capital R upon n raised to 1 by 3. Therefore, taking square on both sides, r square is equal to capital R square upon n raised to 2 by 3. Therefore, the change in the area dA will be n into 4 pi r square minus 4 pi capital R square, which is equal to 4 pi n r square upon n raised to 2 by 3 minus r square, which is equal to 4 pi capital R square n raised to 1 by 3 minus 1. Therefore, dA will be equal to 4 pi r square 1000 raised to 1 by 3 minus 1, which is equal to 4 pi r square into 9, which is 36 pi r square. Therefore, the correct answer is option B. The work done in breaking a big spherical drop of water into n smaller drops, each of radius r, is proportional to, here are the options. Now, the, the volume of the big drop is equal to the volume of the n proportional small drops, which is n into 4 by 3 pi small r cube. Therefore, r will be equal to r upon n raised to 1 by 3. Therefore, r square will be equal to capital R square upon n raised to 2 by 3. Now, the work done will be given by 4 pi r square n minus 4 pi r square into t, which is 4 pi n capital R square upon n raised to 2 by 3 minus 4 pi capital R square into t. Therefore, the work done W is equal to 4 pi capital R square t into n raised to 1 by 3 minus 1. Therefore, the work done is proportional to n raised to 1 by 3 minus 1. Therefore, here the correct answer will be option C. The potential energy of a soap film formed on a frame of area 5 into 10 raised to minus 3 meter square. The surface tension of soap solution is 30 into 10 raised to minus 3 Newton per meters. Here are the options. Now, the potential energy is nothing but the work done, which is equal to 2 into T into A. Therefore, substituting the values, we'll get 2 into 30 into 10 raised to minus 3 into 5 into 10 raised to minus 3, which is equal to 3 into 10 raised to minus 4 joules. Therefore, the correct answer is option C. The energy needed in breaking a drop of radius r into n drops, each of radius small r, is, here are the options. Now, we know that the volume of one drop is equal to the volume of n drops. Therefore, 4 upon 3 pi capital R cube will be equal to n into 4 upon 3 pi into small r cube. Therefore, capital R cube will be equal to n into small r cube. Therefore, small r will be equal to r capital R upon n raised to 1 by 3. Now, the energy needed will be equal to T into 4 pi r square n minus 4 pi capital R square, which is equal to 4 pi T into n r square minus capital R square. Therefore, here the correct answer will be option A. A water film is formed between two straight parallel wires, each of length 10 cm and separated by 5 mm. What will be the work done if the distance between the wires is made 6 mm? Here the surface tension of water is given as 72 dynes per centimeter. Now the work done is given by the formula W is equal to T into the change in the area. Therefore, T is given as 72 into 2 into 10 into 0.1, which is equal to 144 ergs. Therefore, here the correct answer will be option C, 144 ergs. A wire of length 10 cm is gently placed horizontally on the surface of water, having a surface tension of 7.75 into 10 raised to minus 3 Newton per meter. What is the force required to pull up the wire from the water surface? Is it option A 10 raised to minus 3 newtons, or B 1.5 into 10 raised to minus 2 newtons, or C 0.5 into 10 raised to minus 2 newtons, or D 2 into 10 raised to minus 3 newtons? Now we know that the force required F will be equal to 2 into tension into the length. Therefore, substituting the values 2 into 75 into 10 raised to minus 3 into 10 raised to minus 1, which is equal to 150 into 10 raised to minus 4, which is equal to 1.5 into 10 raised to minus 2 newtons. Therefore, the correct answer is option B. Two capillaries are dipped side by side in a beaker containing water. It is found that the rise of water in them is up to heights of 1.3 cm and 3.9 cm respectively. The ratio of the radii is 1 is to 3, 3 is to 1, 1 is to 4, or 4 is to 1. Now we know that h is inversely proportional to the radius. Therefore, h1 upon h2 will be equal to r2 upon r1. Therefore, r1 upon r2 is equal to h2 upon h1. We know the values of h2 and h1, which is equal to 3.9 upon 1.3, which is 3 is to 1. Therefore, the radius will be in the ratio 3 is to 1, which is option B. Surface tension of water is equal to 72 into 10 raised to minus 3 joules per meter square. The work done in splitting a drop of water of 1 millimeter radius into 64 droplets is, here are the options. Now, the volume of the big drop 4.3 pi r cube is equal to 64 into the volume of the small drops. Therefore, our small r cube will be equal to capital R cube upon 64. Therefore, r will be equal to capital R upon 4, which is equal to 1 upon 4 millimeters. Now, the initial surface energy E1 will be equal to 4 pi T into R square. Final surface energy will be 64 into 4 pi T into small r square. Therefore, the work done will be equal to 4 pi T 64 small r square minus capital R square, which is equal to 4 pi T 4 into 10 raised to minus 6 minus 10 raised to minus 6, which is equal to 12 pi T into 10 raised to minus 6, which is equal to 2.7 into 10 raised to minus 6 joules. Therefore, here the correct answer will be option B. 8 equal droplets of water, each of radius small r, are falling through air with a terminal velocity of 7.5 cm per second square. The drops coalesce to form a big drop in air. What will be the terminal velocity of the big drop? Here are the options. Now, the radius of the big drop is calculated by using 4 upon 3 pi r cube, which is the radius of the big block, 8 into 4 upon 3 pi into small r cube. Therefore, capital R is equal to 2r. But the terminal velocity is directly proportional to the radius square. according to Stokes' law. Therefore, V2 upon V1 is equal to K into 2R the whole square upon K into R the whole square, which is equal to 4. Therefore, V2 is equal to 4 into 7.5, which is 30 centimeter per second. Therefore, the correct answer is option D.